Hi, I'm John Windust, and this is my presentation on using random matrices for high accuracy SVD approximations. These methods come from Halko and Martinson's paper, Finding Structure with Randomness, Probabilistic Algorithms for Constructing Appropriate Matrix Decomposition. My sections are going to include the exact SVD or the traditional SVD, the Gaussian method, the power method, the discrete and fast Fourier transformation, the subsampled randomized Fourier transformation, and speed and error comparison of these methods. Then we're going to do a real application and some thoughts. The SVD is a matrix factorization of matrix A, right over here, that results in the decomposition of U, sigma, and VT, or V Hermatian. If A is complex, which just means like the conjugate, and if A is complex, then you can also just take the conjugate and then the transpose. These matrices have different meaning depending on the analysis you're doing, but the basic structure is that U and V are orthonormal bases, which means each dimension is perpendicular, and they are normalized, which means each vector in the matrix has a magnitude of 1. These are U and V are often referred to as left and right vectors. Sigma represents the energy of the pattern in A. This matrix is sigma is diagonal, it's positive, it's ordered largest to smallest, and the number of singular values correlates to the rank of matrix A. The SVD is used for a lot of different things, like PCA, image and video recognition, like facial recognition, data reduction, statistical linear regression analysis to AX equals B problems, and noise removal, and also a lot more that I don't even know about. However, there's some issues with the exact SVD. I'm going to try and refer to the traditional SVD as the exact SVD for clarity. The exact SVD is very accurate, and its error mostly comes down to floating point numbers. You can increase the floating point calculation for improved accuracy, but it only makes calculations slower. It can already be computationally expensive as matrices scale. Halko and Martinson's methods use randomized methods to quickly find the Q matrix so that we can make the factorization of matrix A equals BC. See that B is going to be a tall, thin matrix, M by KS, and C is going to be a short, fat matrix, KS by N. K is just the target rank, if you know the rank, and S is an oversampling parameter. So because C is a short, fat matrix, it will calculate the SVD much faster on C than on A. And that's what these methods do that we're about to talk about. Excuse me. Oops. Okay. Our first step in the Gaussian random matrix method is to create the Gaussian random matrix G. G is an n by L matrix composed of elements of the Gaussian random distribution. My data is images, and grayscale images or any image data point, ranges from 0 to 255. So I chose a mean of 127.5 and a standard deviation of 19, because it takes over 6 standard deviations to create an element outside of that range that I want. When I refer to L, it's referring to the rank plus the oversampling parameter. For this method, the oversampling parameter, he just recommends 5 or 10 as a starting point. All right, once you've created the G matrix, you multiply A times G to get Y, and then you just take the QR decomposition to get your Q matrix. You can then use matrix Q to create C, like previously explained. Yeah. To fix okay, sorry. The power method improves accuracy compared to the Gaussian method. By squaring or cubing A, you can increase the accuracy with pretty minimal computational cost, because you're just squaring or cubing the elements inside of A. For m by n matrices, you can make the matrix square by multiplying A times A transpose, but there's an issue with squaring or cubing matrix A with either of these methods, and that is the floating point errors increase, which can lead to even worse error when you're trying to get even better error, as I had until I realized that Halko and Martinson's paper actually explains how to fix this issue. To fix this, you need to orthonormalize the columns between each step or each application of A and AT. This is actually too bad in a way, because it added a bunch of QR decompositions to the calculation, which slows it down, but it still ended up being faster than the exact SVD method for finding Q. And if you look at this, I'm hoping you can see my mouse. So the first step is the Gaussian method, QR stop condition for the Gaussian method, and then you're just taking that Q and doing A transpose times Q, and you just keep doing that QR, dropping down stop condition for Q1. Pretty cool. Okay, so I didn't have any knowledge of the discrete Fourier transformation or the fast Fourier transformation before I did this project, but you need to know how it works to understand the SRFT method coming up. So we're going to start with the discrete Fourier transform briefly. It is a matrix multiplication. That's a coordinate transformation of a vector into an orthogonal basis of sines and cosines. So let's look at how to create the DFT matrix. We're just gonna start with a matrix that we would multiply by a vector of length 4. That's why you see the subscript 4 on the omegas, but we'll talk about the omegas more next. You can see the J and K indexes that are being multiplied by each other to create the matrix on the far right. Now omega is related to the sines and cosines in the Euler formula, and that's where the idea of the new basis comes from, or the sine and cosine basis. You can see the calculation below for calculating the omega on the bottom. From omega 4 we get negative I, and with Euler's formula you can see that it's a negative pi over 2 rotation, which is related to a negative pi over 2 rotation on the complex unit circle. So you can see on the complex unit circle that as we move negative pi over 2 rotations, we get all the omegas needed for the calculation for a vector of length 4. So you can see that we can substitute our omegas into the omega matrix that we created earlier. You just need to remember that the complex unit circle is periodic, and on the right is the final DFT matrix for n equals 2. You can just put a column vector on the right of length 4, matrix multiply, boom. Okay, so this is the generalized discrete Fourier transform equation, and you can see that vector f after multiplication will turn into its new frequency domain f hat. F hat is called the Fourier coefficients of f. This works, but as the matrix scales, it gets bogged down in large matrix multiplication. However, there is a faster way. So I looked at, let me back up. There are lots of different methods to calculate a fast Fourier transform or transformation, but I studied the decimation in time fast Fourier transformation based on the algorithm of Cooley-Tukey, which is from 1965, which every book will tell you. So first we're going to find the length of the vector. Second, we're going to reorder the vector into its bit reversal, calculate and apply the omega, which is also called a twiddle factor, to every odd pair, add and subtract pairs, repeat steps 3 and 4 until we get to the base case. Okay. Now imagine we have a vector of length 8, and we call it 7 computer science style with in zero indexing. Now, to make it simple, imagine the vector's elements is the same as the index, just to try to make it more clear. Step 2 is to reorder the vector into its bit reversal. This just means that you break each element into its binary with a width the size of your largest index binary width. That's something I did wrong until I realized you got to do it that way. Then reverse the binary, then convert it back to its reordered integer. This this relates really well to something called a butterfly diagram, but it would take too long to present. However, writing out the butterfly diagram over and over and over, I came up with a great diagram of how this works, or how the whole FFT works. DIT FFT. Okay. So I made this. I think it's the clearest explanation I've ever seen for the calculation of the FFT without double calculating, like in the butterfly diagram. I think this is honestly my best work in the whole project. I spent a lot of time on this. Before I got through this, before I go through this, just imagine this as you having one matrix and you're performing operations on it and creating new rows and or replacing rows instead of creating tons of matrices. So, hope you can see my mouse. So, at the top we just have calculating twiddle factors. It turns out for the FFT you only need half the twiddle factors. That speeds it up. So right here we have the bit reversal. Boom. Apply the twiddle factor to every odd, which this one's really easy. 1, 1, 1. Add pairs. Now, is subtract pairs, right? It's just like doing a VStack in Python. We're adding the pairs, keeping the matrix, the row, we're just replacing the row, and the subpairs, we're just adding a new row with the subtraction of pairs. Now this is repeating those two steps again, just like I said. Apply the twiddle factor to odd elements, then add pairs, add sub rows, and again, and this scales to any size. Really pretty cool. Okay. So, DFT versus FFT speed comparison. So, based on 10 runs when possible, due to calculation times, it's clear that the DFT is much slower than John's FFT and NumPy's built-in FFT. My scaling is off, though. I realized this is due to the way I coded it. Had the right idea, but I have a nested for loop, which is ruining the scaling and making it really slow. And it's taking away from basically the speed I intended it to go. Also, NumPy's FFT is super optimized, and I'm just learning, so I guess I shouldn't be surprised I didn't beat NumPy's FFT. Pretty cool, though. Proud that I was able to self-learn that. Okay, so now that we have the understanding of the DFT and the FFT, we can get into the subsampled random Fourier transform. This method creates a random matrix faster than the Gaussian method. It's really kind of the same idea. So we want to create a random matrix omega, where omega equals the normalization factor times DFR, where D is basically just a diagonal matrix with a random point on the complex unit circle. This is the randomization part of SRFT. F is a DFT matrix, like we previously discussed. R is a sampling matrix, where the columns are L samples of the identity matrix of size n by n without replacement. we can speed up the creation of the omega matrix by taking the FFT of dr instead of using the DFT. Then we just multiply A times omega to get Y, and you take the QR just like we did in the Gaussian method. I think it would be interesting to apply a power iteration here, but that wasn't in the Halko-Martensen paper. Okay, to test these, I created random grayscale images with fixed rank that I then targeted, that rank. You can see one of the images behind the text speed and error comparison. These are all computed 20 times on the paid Google Colab server with 334 gigs of RAM to speed up the calculations. In terms of speed, the Gaussian method for this test was the fastest. The slowest were the base cases and the super slow nested for loop inside the John SRFT method just killed it. Note that all the methods would have calculated even faster if I had put the NumPy SVD on C instead of John's exact SVD. But I used the one I wrote. When looking at the error, I was actually a bit shocked how accurate Halko and Martensen's methods were. If you examine the reconstructed vectors, the reconstructed matrices, and you look at the vectors that actually have rank, the linear and independent vectors, it was like, you'd see 129.9999 versus the original data of 130, which I thought was pretty impressive. Some of the methods even outperformed the NumPy, exact SVD in terms of error, which was really surprising because I thought this was just going to be comparing huge error to a somewhat perfect base case, which really just meant that they had high. I tested all of these with really high floating points. So for a real, my real application speed comparison. So to do a real application test, I tested the truncation speed of a full rank matrix. That's an SVD truncation. I chose the most famous matrix I could think of, the Mona Lisa. This is a high-res image, and because there are 3 colors in the image, it has to be done. These methods have to be done on over 130 elements. I chose 1,771 as a target because I already knew it captured 80% of the sum of singular values, and I assumed my high definition image had a bunch of noise in it. So this tests the methods, or this also tests the methods on a non-square matrix. The speed results were actually different. This time SRFT using NumPy's FFT was the fastest, which is more in line with Halko and Martensen's paper. That's supposed to be the fastest. However, my function with my FFT remained the slowest, and everything else still totally beat out the base methods of NumPy exact SVD and John's exact SVD equation. So So this table shows the memory reduction based on singular value capture. Tau is something briefly discussed in my paper that I cut out of my presentation, but it's the optimal threshold for Gaussian noise, a paper by Gavish and Donahoe. Pretty cool. Notice this 20% sigma capture is a 96% reduction. Okay, honestly, the differences between images are a little more clear when you can make them bigger, but there is a small reduction in quality, particularly starting in the middle and going right. But I found that the 20% reduction, the 20% sigma capture and 96% data reduction, I was surprised you could even see the image still. But yeah, really cool stuff. I had no idea how to do this before the project. So just some final thoughts. All the methods performed better than I expected. I expected them to be faster, but not as accurate as they were. Also, all of his testing was on MATLAB, which I think is like all programmed in C. So I think it probably everything goes even faster in that than in Python. Also, just a lot more experience coding there, I'm sure. Although these methods were not designed for rank truncation, they're really designed for low rank approximations, because you don't want that queue to basically create another giant large matrix. You're not saving any time, so that's a giant square matrix. It still worked really well for the SVD truncation. I thought it was really cool. It'd be interesting to explore some things I cut out that I plan to do, including more testing on oversampling parameters. They do go up, or error does go up as you oversample more, and speed goes down. It'd be interesting to see if that's like a linear thing or something else. And then I was just kind of curious if all these random matrices are adding some kind of Gaussian noise, particularly the Gaussian random matrix. But other than that, it was really cool. I really appreciate your time if you watch this, and I really enjoyed it. So thank you very much. Again, I'm John Windust. Have a great day.